In this episode, we are going to simulate splashes colliding with the buildings. I'm going to start with the right side. Let's first extract the source. There are various ways. One is to extract the tsunami mesh where it intersects with the buildings, or you can simply put a box behind a building as the source. Both will work. So we just find out the better option as per the shot. Here I like to apply the first way. Import the tsunami mesh and the collision object. The collision object is in VDB format, converted to polygons. We can optimize it further. Next, I'm gonna color the tsunami and the buildings for an intuitive view. We add an attribute transfer node and transfer color only. A smaller distance threshold is fine. Then display the buildings. Still, we start the simulation from the near buildings. Okay, this one first. Let's suggest distance threshold as per the case. Then extract the red area. Next, we add a box to box up it. I'm gonna delete this part, which is not in the camera view. Then we optimize out the part within the buildings. So does the front part. Because the tsunami only hit the back of the building, we drop one more box up the front part, and delete it. Meanwhile, the source should be still rather than moving. So let's fix it when the tsunami intersects with the building. This place. Okay, done with it. Then we add a poly extrude and extrude it down so that it can be hidden under the tsunami. Cool. Add a clean node to remove the unused points. Then we drop down a dot network. Let's start solving from the first frame. That is, when the tsunami just collides with the building. We enable .NET 1. Hit particle fluids. Then two geometry nodes are added. This one is for exporting flip. It's useless, so we delete it. We copy these three nodes and paste them in one geometry, which can make the things easier for some operations. Now the source is ready. Uncheck shell thickness. We don't need it. Then drop a point velocity. Tick add curl noise and add velocity. When it comes to the val, we can refer to the tsunami animation. I remembered that val was set to $f, that is 30 meters per second. A similar value is fine. Show the val lines. Well, they're abnormal. We select Keep Incoming for velocity. There are no velocities imported. Only the velocity we set here is displaced. Similarly, set the value on y-axis to 25 and set a smaller value on z-axis. Because the tsunami is moving obliquely, we will adjust these parameters further in simulation. Set swirl size by referring to previous value. As for the scale, it's fine as long as there is some variation on the edge of the val lines. Turn up turbulence slightly to bring some more details. Perfect. Currently, The source keeps emitting particles all the time, so we need to set a time period. We let it stop emitting particles after 5 frames to limit the quantity of particles. Next, we set up the fluid box for the simulation. Drop down a box. Here we align it with the ground. Then we connect the center and the size of flip solver 1 with box 33. We've demonstrated this before, so it just quickly set up. Solve 1 frame. Okay, it goes well. Let's first add the necessary nodes, such as gravity and static object. Select Use Volume Collision, which supports VDB format. We import the VDB volume of this building. Check on Collision Guide to show them. Oops! The mode here is wrong. It should be Volume Sample mode. Alright. Then up the friction of flip object. As to the particle separation, we can still refer to the value in the previous splash simulation. That value is 0.2. Since the splashes come from collision with one building, it's better with more details here. So we keep this resolution for now. Then let's go to the optimization. We still delete particles beyond the camera view and those inside the Tsunami. We can copy the settings from the previous process. Del 1 is the range of killing the particles inside of Tsunami. Copy it. We reduce the value on X and Y offset a bit. Then we set up the flip solver by referring to the previous simulation. Change the max substeps to 1 and check on Detect Jobless. Here we set a smaller value for velocity smoothing. The surface extrapolation is to control the degree of adhesion between the fluid and the collision object. The larger the value, the stronger the fluid is adhering to the collision object. So turn it down a bit. Alright, no further settings. Next, we add a pop drag for the particles with the droplet attribute above 0.8, then duplicate it for all the particles. Still, we refer to the previous setting. Then add noise to the flip simulation. In addition to adding pop force, you can also add a noise node. I'll demonstrate for you in SUB. Drop down a current noise. Add a vector to vector 4. Connect it to time. Then the current noise is animated. Connect it to color to take a look. Set a lower frequency for noise so that its scale can be larger. Set a lower roughness. Increase amplitude a bit. For this current noise, we mainly want a large noise. We duplicate it. For this one, we want a small noise, so set a large roughness. A small amplitude is fine, and set frequency to 0. The small noise is mainly to add details, and the large one is to affect the strength of the small one. Drop down a fit to control the large noise. Lastly, multiply it with a small noise. Now the small noise has various strength, and we can adjust the parameters here to vary it. We copy this chain and paste it into the DOP and connect it to force. Uncheck pack particles. I'm not a big fan of this function. It just compresses the particles before saving them into the disk, which may save some space. But the unpacking process is a bit too time-consuming. If you don't have enough disk space, you can check this box. Before caching, I'm going to compress all the attributes except position. Then we set up the file cache, connect a start frame with the .NET one. We cache it out. It's done. Let's check it. Good overall, but one concern. The splashes fly too far away from this building, which is unreasonable. Let's find a better perspective on what's going on. The splashes hit the building and fly over the building to this place. This distance is too far, and the height is also too high. So we need to limit them. Drop a pop wind. Set the wind velocity in the opposite direction, that is 20 on the positive x-axis. Then set a value on the negative y-axis. Add some noise to get more details. And then set a positive offset animation on the y-axis to make it more noisy. As for the noise and the wind velocity, they are influenced by the air resistance. The larger the air resistance is, the higher the wind velocity and the noise act on the particles. If we set the air resistance to 0, then the wind and the noise won't work. To let you guys better understand it, I set up a simple project. Currently, these particles move forward at a constant speed. We add a pop wind. By default, the air resistance is 1. Then the wind field takes effect quickly. When the wind velocity is 0, the particles can decelerate quickly. If we turn down the air resistance, the particles will keep the original speed more easily. So does the amplitude of the noise. If we set the air resistance to 0, then the wind and noise don't work. And the particles retain their movement. So if you want the wind or noise work obviously, you can set a larger value. But if too high, it may lead to unnatural dynamics. Anyway, you can test the result in simulation. Besides, we need to set the time when the collision object is disabled. Imagine that if the splashes keep intersecting with the static object, when we change it to a fractured building, the boundary of the splashes won't match the outline of the building well. So to avoid that, I prefer to disable the collision object in the later stage. At 45th frame, we let the collision object disappear. Good. Another problem is a splash is coming out from under the building, which is unreasonable, so we need to delete it. Besides, though we've deleted those splashes beyond the camera view, we can still delete more on the x-axis. And we can delete the splashes under the bottom of the building. Create a boundary here. Let's extract the bottom of the building through normals and height. Then extrude the volume. OK. Import this volume into DOP. We directly merge the existing groups with the same name. Good. We simulate it to take a look. The lower one is the effect after modification. Compared with the previous dynamics, the splashes are much weaker in terms of distance and height. They look reasonable now. So far, there's no collision with the tsunami, but I'm not going to add it anymore. Instead, I'll make other splashes colliding with the tsunami. The extra splashes under the bottom is fixed. Perfect. Let's move on. I'd like to emit mist directly with flip. If it looks good, we needn't simulate the whitewater. The process of mist creation is the same as before. We simply copy that chain, set the variable based on the velocity to act on the variance here, adjust the inherent velocity slightly to add some randomness. The parameters here needn't too much modification. The current quantity of particles is fine. Jump into subsolver. No need to delete particles inside the surface field. Keep this node. We replace the ground with the tsunami. Let the mist fall on the ocean surface. Get the start frame of file cache and DOP linked. Start from the first frame. Match the stop with the one above. Okay, we cache it out. Okay, this is the mist simulation colliding with the tsunami surface. It's a bit diffuse and scattered, so it's unnecessary to add the tsunami collision object. We can see the particles here were killed because we applied this range for killing particles. Actually, we should use the range that shrinks inward, so the particles dropping on the tsunami won't be removed like that. Currently, I only applied the tsunami and skipped the buildings. Because the water mist is relatively large, I'm afraid its simulation boundary with the buildings won't go well with fractured buildings. So let's cache it again. Alright, the water mist on the ocean surface goes well now. We're done with the splash. As to the rendering settings, we directly copy them from the previous process. We'll adjust them later. Let's go ahead. Move on to this building. Copy the workflow we made just now, as well as the fluid box here. I'll simulate splashes individually for each obvious building in the view, and apply different types of source accordingly. So here we won't use the same DOP. Well, we first set the source. The source here is dynamic, as the tsunami intersects with the building. I think it would be better if we emit some particles on the sides of the building, so we keep the sides. And we still delete the source inside the building. These are useless. Delete these nodes too, because I want the source to keep emitting as long as the tsunami touches the building. Besides, there is a problem here. Take a look at the splashes. They are actually in the front of the tsunami, that is, they touch the building first. At about the 50th frame, the water splashes have already hit the building. If the source exists only when the tsunami intersects with the building, it won't come out well. Instead, it should be there when the splashes start to hit the building. So we still need to add a fixed source around the 55th frame, when the splashes just touch the building. Set start frame of depth to 55. When the ocean surface touches the building, we disable the fixed source and enable the dynamic source. This way the collision can be more reasonable. Since the source keeps emitting, we reduce the velocity slightly. Let's go through the depth. Randomize the current noise one a bit to vary from the first one. Same to the current noise too. Also adjust the parameters in the fit node slightly, but the best way is to adjust them in sub for an intuitive look. Then copy the values to depth. Considering the source keeps emitting, in case it's too intense, we bring up air resistance. Let's check out the sub-solver into camera view. The source is here, so these two nodes are not needed. Keep the parameters in pop wind and the simres. We don't have to switch the collision object for now. Bring down this parameter slightly to avoid too much fluid sticking to the building. The other parameters are okay. Let's move the box. Then we cache it out. Alright. There are some obvious issues in it. One is that the dynamics are not fierce enough. The other is that the amount of particles is not enough. Most of them were covered by the tsunami. So we can multiply the velocity of the source and lower wind velocity in pop wind one slightly. As for the amount of particles, we can either bring down the particle separation or bring up this parameter so that particles can be held a bit more in each voxel. Now we can roughly know the collision object can be removed at around the 85th frame. Then we cache it. Alright, it's better now. Hop into the camera view and make a flipbook to check the dynamics. It goes well generally, but still can be refined. Firstly, the overall height of the splashes is a bit high, which doesn't make perfect sense. Secondly, the clumps are a bit too obvious. I want more scattered particles like this. Let's start to lower down the height first. Simply increase the wind force in the negative y-axis. For the clumping issue, we can either increase max particle density slightly or mean particle density. Here I like to share how the detect droplets works. Detect droplets can break up tendrils on the leading edge of splashes, giving them a more diffuse look. When the surrounding particle's density is less than mean particle density, the particles will be regarded as water drops, which can be less influenced by fluid forces. Likewise, when the surrounding particle's density is greater than max particle density, the particles will be regarded as fluids, which can be completely influenced by fluid forces. So both of them will do this job. No other adjustments needed. Let's cache it. Okay. The overall dynamics are not much different than before. Just the height is lowered slightly. Compared with the previous version, so far so good. Let's continue. Link the start frame in top with that in the flip. No changes needed here, because they're already set properly. I prefer disconnecting the collision object, the Tsunami. Do not forget to get rid of ID 0 here. Previously, the ID of the collision object was 0. If the collision object is removed, the ID of 0 will represent the particles. That is, the particles will be excluded wrongly. Now we cache it out. Okay. It looks good overall. Just the particles below the ground should be deleted. And the particles are a bit few. Let's work on them. For the first issue, we add a pop wrinkle to delete the particles whose position is less than 1 meter. Then we increase the number of particles. Also, we copy this pop wrinkle to the previous simulation. We will cache it later and continue to see how this pop simulation comes. Okay. It goes well now. We're done with the first two simulations. Not much difference except the source. The rest of simulations can be dealt in the same way. So I won't demonstrate them one by one. Let's just do a quick walkthrough. We simply change the source. And tweak the parameters as needed. I made some different settings regarding this simulation. Here I multiplied the velocity and then added a turbinoise to it. Display the velocity lines. I varied the outline of velocity lines through turbinoise so that the splashes can generate more variations. Get into DOP and pop Vob 1. I added wind force on the negative x direction. This way the splashes can fly farther. Besides, the edges of this simulation are a bit too long, which is not good. So I deleted some fluid based on real point B-box. ID attribute was applied here, so I added the ID attribute in the simulation. Before caching, drop in the attribute to be compressed. we cannot compress the ID attribute like before. Let's come down over here. The water mist on the edge is a bit less, so I added another simulation. The same way with the previous one. Got them merged in the end. We also made some specific adjustments for other mist simulations accordingly. For this one, some particles at the top are deleted because they're too loose, and the water mist emitted by them won't look good. Briefly speaking, all settings are for the effect. Now we merge them together and make a flipbook. Alright, it looks powerful overall. This building is in the center of the view. To highlight it, we added a wind force on the negative x-axis to make the splashes more fierce. As for the particles intersecting with the buildings, later we'll simulate the building destruction to cover them. So it doesn't matter here. To check out the whole fluid simulation, let's render it out. Get down to the rendering settings. Here I have set the render range for each simulation respectively. It's simple, so I won't demonstrate it. As for the process of compressing volumes, we can deal with them together for a cheap rendering. Then we import these two parts into a new geo. Duplicate two file cache nodes, rename them, keep the original materials. These two were created by accident. They are useless, delete them. Then we set the objects to be rendered. No more changes. So let's render it. Alright, it's done. This is the 85th frame when the main splashes fly. The only problem is that the water drops are too large. We need to lower the p-scale values. Here they are. We reduce them by half. The water mist looks good. Just keep it. We render it again. Okay. It's more delicate than before, with more details. I also rendered a few more frames. If you want a more detailed and delicate look, you can increase the simres a bit more. But we don't deal with it until the final rendering. So far, so good. We can get down to the next stage. See you next time.